Yo, what up? Welcome back to the floor of my lab. I was at the store the other day and I saw this cool piece of hardware sitting on the shelf for about $35, a nice modest price. And if you know anything about me, you know that I can't pass up a good piece of hardware. So this is a macro pad-like device with 12 customizable buttons on the front, with a display that sits behind those that you can put pictures on and customize to your heart's content. So I get this thing home and I plug it up to my computer and guess what? It doesn't work. If you're anything like me, a fan of self-induced computer-related suffering, that is to say a Linux user, then you're probably familiar with spending way too much time trying to get your new $35 Hack the Box challenge working. But as a fan of breaking things to figure out how they work, I decided to take this as an opportunity to brush up my skills and learn a little bit more about this device. So the idea is simple. Get control of this screen and read these button presses, and then I can make this thing work in Linux. So when dealing with USB devices, the first thing I had to understand were the device descriptors. There are various tools that can be used to query these device descriptors, but in my case I just used Linux's LSUSB tool. These descriptors describe the various transfer methods that we can use to talk to this device. These descriptors also describe the transfer rates and the buffer sizes. Now I want to capture some data that's going between my computer and this device, and for that I'm going to use Wireshark with USB PCAP. Something interesting to note is that when I use Wireshark to capture this data, I won't be seeing the individual packets that are going between the host and the device. Instead, Wireshark will capture the entirety of what the USB host stack sees, and these are called URBs, or USB request blocks. During this, I started to understand the data a little bit more through a process called behavioral analysis. By initiating actions within the native software and capturing those request blocks, I'm starting to notice some familiar patterns. Now that I've captured a ton of data, I'm left with one question. What does any of this mean? It seems that the first few bytes of this vendor data corresponds with an action or feature of the device that we can call or take. And then the rest of the data appears to be parameters or information that modifies that function or feature. Sort of like a function or method call within traditional programming. If I want to learn more about this vendor-specific language that the device speaks, then I'm going to have to dig into their software a little bit deeper. After looking at the files on disk, I noticed an interesting executable called the Mountain Display Pad Worker. I used PE Studio to do a little bit of static analysis on this binary, and it informed me that it's likely coded with C#. It also showed me some external libraries that were being referenced, one of which seemed pretty juicy. That's the DisplayPad SDK.dll. After learning that the DisplayPad Worker service was written in C#, I tried to decompile it using a tool called IL Spy. In general, C# programs are not stripped of their debug symbols when they're compiled, and this gives tools like IL Spy the ability to reconstruct the decompiled output in a lot more readable and verbose way. This turned out to be very helpful. This proved to be incredibly useful as it later informed my analysis of that DisplayPad SDK DLL file. Unfortunately, IL Spy isn't going to help us a whole lot with this binary, so I decided to throw it into Ghidra. One of the first tasks that I had for myself in Ghidra was to hopefully identify some of those bytes that I had seen in the URB data that I had captured earlier. Most of the assembly and decompiled output from Ghidra was a lot harder to understand than the beautiful and wonderful output of IL Spy, with its symbolful decompiled output. So believe me when I tell you it makes my head hurt and my eyes bleed to deal with all that Ghidra. Thankfully that didn't take long, because as I started to cross-reference the output of IL Spy with Ghidra, it started to make a lot more sense. Most of the functions in this DLL file go sort of like this. Take some parameters, squish and pack those into a message, and ship those off to the device using the device handle. So now that I know the general structure of this DLL file, all I need to do now is reverse engineer the functions that are necessary to use the device. Sounds easy, right? Controlling the screen seemed like the biggest challenge of them all, so I kind of wanted to tackle that one first. In my testing, I identified one vendor header that seemed to correspond to functions that set and change the display data. This header aligned with the set panel image and the set icon pick exports from the DisplayPad SDK.dll file, so I decided to dig into those. With the Python USB and the Python pillow library, I decided to set up some rudimentary code to test out these image functions. Using the transfer method and the endpoint details that I learned from the descriptors and the captured data in Wireshark, I smashed my head against this code until it didn't work. After being stuck at this point for what seemed like days, I was not sure if I was going to decipher this encoding structure that they used to send images to the device. That was until I sent a completely red test image. After I sent that test image, it immediately dawned on me as I started to see a pattern form in the data that I was capturing. In hindsight, it's pretty obvious, but this device is expecting me to send it the pixel data, RGB values, in byte form for every single pixel in the image. So what I need to do first is take my image and convert it into an array of RGB pixel values, then break that data up into 1024 byte chunks, because that's how big our transfer size is, and we feed those to our device over and over and over until it times out. And we open that. Okay, so that should all be the same. Let's try this again. Hey, look at that. Okay, so I think that's the hardest part out of the way. Now I've got to listen to these button presses and send some keystrokes or do some stuff, and then it'll be just like the real thing. So using the same Python USB library, I should be able to listen to one of those endpoints that the key presses are sent over, and then map that to a key press table. So let's give that a shot. I could spend more time dissecting this data that's coming from the device, but I thought it was a lot easier to just capture the entire frame and stick that into a table and use it as our mapping. If there's one thing you'll reverse engineer after watching my videos or streams, is that I am lazy. Very, very lazy. Now that I've got those button presses being detected, I can wrap all of that in some code that will take a config of keystrokes and or system actions, and then execute them depending on which button you press. So like most of my projects, I tend to get to a point where I feel pretty satisfied with the lessons learned and the knowledge gained, and then I'll move on to something a little bit more captivating. For this one, however, I decided to take it a little bit further and write a little bit of extra code just to make this device a little bit more usable. After all, I do want my $35 Hack the Box challenge working. I've also gone ahead and posted this code up to GitHub for you all to use, review, and possibly contribute to. Anyway, I hope you learned something from this video, and hopefully it inspires you to start asking questions about your own hardware and software, and maybe even start doing your own reversing for fun one day, whichever comes first. Bye!